Cool. Okay, so let's get started. So our speaker today is Dr. Changhyun Cho. Uh, Completed his PhD last year from New York University and is now a joint postdoctoral associate at both MIT and York University in Toronto. Changhyun has worked on galaxy evolution, black holes, machine learning, all kinds of things. But today he's come to give us an introduction to actually the THESAN and THESAN-Zoom suite of simulations. And this is actually the first time that CaTS has highlighted a simulation project. So we're actually very excited to be opening up this new chapter. But I'll stop talking whenever you're ready. I'll let you take it away.
All right. Yeah. Thank you, Nolan, for nice introduction. Hi everyone. My name is Changhyun. I'm a postdoc researcher at York University. So today I'm going to talk about some more practical guide to THESAN and THESAN-Zoom simulations. Yeah, I heard that you guys so far this is the first theoretical or numerical seminar, so I'm very honored to give it a first one. And because I know I just assume that most of the speaker here are mostly the graduate students, so they are not we are not super familiar with the simulation. So the first part of the this seminar talk will be just to give. I'm just gonna give you some introduction about the cosmological simulations, and then I'm gonna move on to the DSAN and DSAN-Zoom, and also we have another next generation DSAN simulation called Lumina. We're gonna upload our first papers from next week. So I'm gonna talk about that one as well. And then, for those who are interested in working with the simulation or want to use the simulation data to compare it with your observational data, then I'm also going to show you how to how to use the simulation data for your research. Okay, by the way, feel free to interrupt me at any time if you have any questions. I'm always happy to answer. Okay, so let's go to the introduction to the cosmological simulations. So why are we using the simulation and why are we simulate the universe? Because we want to we want to interpret the observations because using the observation, we're gonna get some lots of data and we want to understand how they work, how they form those kind of structure. So to do that, we have our physics model like galaxy formation or dust creation and all those kind of thing. We just want to know how they are formed. And also, personally, I think this simulation is a thought experiment because as long as we have a fair understanding about the physics, like how the gravity works, how the fluid dynamics works, as long as our understanding about how galaxy formation model is correct, then if we put everything into our simulation and run it to the redshift 0, or redshift 3, then what we simulate will be similar to the observation. And that's if the result is similar to the observation, then our understanding is correct. But sometimes, actually many times, the simulation result and the observation result are not always the same. That's actually more exciting because we can know about our discrepancy about our model. So that's also something we are doing the simulation. And another thing I also want to mention is because the all lots of interesting physical phenomena is actually happening the very subparsec scale, like how stars form and how black hole is formed, how they put the energy through the environment. Yeah, these are subscale structure, but these subscale physics phenomena can influence the whole evolution of the galaxy. So we want to bridge the gap between small scale physics and the large scale structure formation. And also, not only that, we can also test something else. Like right now, most of the simulations are using lambda CDM model to make the universe, but we can also test another dark matter models like self-interacting dark matter. Recently, many of people are doing that, and also people are doing fuzzy dark matter or the warm dark matter, something else. You can test as much as you want because in astronomy, astrophysics, and astronomy, we cannot experiment just like other science like biology or chemistry. We cannot create the universe. We cannot create the black hole. yet, but yeah, we can test it using the simulation, yeah, using the computational power. So that's what I am interested in, and that's what I'm doing. So yeah, common physics in the cosmological simulation and many of the numerical simulations, we use gravity, of course, gravity, yeah, to describe the motion of the dark matter and baryons. And also we use the hydrodynamics because we want to know the how gas moves. And also we put some other physics like a radiation or magnetic field, especially if you want to, yeah, make theoretical people uncomfortable, then always ask this question. Did you include magnetic field? Then yeah, we will be quite toasted because including magnetic field is always one of the most difficult thing. But in this case, in our simulation, yeah, I'm gonna talk about gravity, hydrodynamics, and the radiation. So how the gravity works? We already know quite well. Yeah, you guys are very familiar with the gravity, how gravity works, the Newton's law and those kind of things. But in this case, we are going to use a slightly approximate thing because if I want to calculate the Hölder force between particles and particles, then because we have lots of particles, calculation would be too much. So what we are going to do is we just assume dark matter and stars are collisionless and non-collisionless particles, and we just use their distribution. And using their distribution, we get the gravitational potential, and using that, we get the acceleration. So, but basic work is basically the same as Newton's law. Yeah. And for the hydrodynamics, yes, we need to solve these differential equations. I'm not sure you guys are actually studied the fluid dynamics before. I'm just gonna simply explain those how things work. So the first row you see is the mass conservation law. So yeah, how the mass works. And the second row is the momentum equation. So how the momentum is conserved or acted by, influenced by the other source vector. And the last law is just the thermodynamics or energy conservation law. So for me, I understand it this way. Yeah, mass is influenced by the mass movement is influenced by the momentum, and momentum is influenced by the energy. I know this is not the perfect way to understand the way, but this is how, yeah, just to briefly want to understand the movement. But you see, there are two columns, even though we are talking about the same equation, continuity, mass conservation equation, momentum, and the thermal equation, but we have a two different form. The first column calls the Lagrangian scheme or Lagrangian form, and the left one is called Eulerian form. What are they and what are their difference? Yes. The YouTube link will be posted from Nolan or anyone else. Yeah, okay. Yeah, sorry about that. So yeah, the first column is Lagrangian, and I think when you look at the simulation, when you talk about the simulation, you heard about those things, grid-based or particle-based. So if you want to look at the how fluid moves and those things, yeah, we usually use a Lagrangian scheme. So simply think of it this way. So fluids are moving, and I want to track those fluids are moving. So I put the camera, and I just track this fluid by moving this camera as well. And the other one is Eulerian scheme, which is the grid-based simulation. And now, in this case, we are not moving the camera. We just look at the same area and see how the fluids are coming in and coming out. This is the way we we are solving and we are looking at the motion of the fluid. Yeah, that's the easiest way we can understand, and that's how I understand. Yep. And yeah, basically we are solving differential equations. Okay, but we know the whole physics quite okay, we believe. We know how gravity works, and we know how the fluid dynamics works. But why do we have so many different numerical simulations? Yeah, when you look at the right side of the picture, and there are so many different simulations, and yeah, you see a lot of them. Okay, so because what we want to see is different. If you want to, so just like doing the observation, yeah, if you want to look at the survey science, then you need to look at the bigger sky. Or if you want to look at the just the individual galaxy or the ISM or the small scale structure, then you need to look at the smaller scale. Yeah, simulation does the same thing. So if you want to get the statistical data, then you need to do the large volume simulations, which is the second row. And if you want to look at the individual galaxy and how they work and how they interact and how they evolve, then you need to look at zoom in simulation, which is the first row. And also physics included can differentiate the simulation as well. If you want to just look at the dark matter halo and how the dynamics of the dark matters, then you need to look at the dark matter only simulation. The reason why we are still doing that is this is computationally much cheaper. But if you want to include more precise how baryons work, how the supernova is happening, how the whole gas particles are influencing the structure formation, then you must put the hydrodynamics, which is this second column. Yes, dark matter plus baryons. So yeah, that's how you can do. So yeah, I think you guys are very familiar with the illustrative simulation or fire simulation. Yeah, these things are the simulation names, and yeah, you will see a lot. And today we're gonna talk about the THESAN simulation. Yeah, also, why I didn't answer the question correctly because why do we still have so many different simulations? Because some specific physics are different. Yes. How can we simulate the universe? Just like we solved the differential equations, we need to start the initial conditions. So usually we put the initial condition from getting the initial condition information from the CMB, yes, CMB information. And then as long as our physics is correct, like put the physics, like gravity, yeah, you already saw the gravity part and hydrodynamics. And then we need to put another model called the subgrid models. And because of these subgrid models, we have so many different simulations because there are lots of different models of the star formation and the black hole physics. So yeah, people use the different physics of this phenomena. That's why we have different names. So as long as our model is correct, our physics is correct, as long as our initial condition is correct and physics is correct, then the result must be the similar to the observation. So this is how simulators understand the universe. So I want to talk about more about these subgrid models because these things are the most important thing. Yeah, subgrid models can describe the physics below the resolution limit. When we are talking about this cosmological scale simulation, the box size is around megaparsec scale, tens or hundreds megaparsec scale. So the resolution limit is around the kiloparsec or 100 parsec scale. But the star formation and the black hole physics, something interesting is happening much smaller scale, like a sub-parsec scale. Yeah. So we want to describe those kind of phenomena, even though we cannot resolve it. So also, still, some physics are not well known. Yeah, that's why we try to put more effective model, yeah, to describe the black hole or stellar phenomena. Or you might have wondering, even though if we know all the physics included, all the physics correctly, then why don't we just make the resolution as small as possible, then run the simulation? Yeah, if you want to do that, we can do that, but the computational time is huge. Yeah, even current algorithm and the current most specific model, using the highest resolution, yeah, it will take almost 10,000 years to completely run the simulation, even using entire Earth computational power. So we need to compromise at some point. That's why we need to use subgrid models. Okay, so for subgrid models, we use yeah, there are lots of physics implemented as subgrid models, like a cooling function, star formation scheme, and how a star is distributing metallicity through the environment, and the stellar feedback, which is a supernova, and the black hole accretion and black hole feedback. Those things are we cannot resolve it correctly, so that's why we put it subgrid models. Okay, so now I think it's time for us to go to, yeah, design simulation. Okay, so design simulation for the gravity part, we use more sophisticated algorithm called 3PM model. So this one, basically the same thing as the solving Boltzmann equation I showed you before, but we first of all, we made more hierarchical structure of the all individual particles. So if you have some particle, test particle, and around them there are some particles around them, and there are other particles far away from these test particles. So which one will influence this test particle more? Short range particles. So in the short range, we need to use more precise calculation of the gravity. And for the long range particles, we just approximate it and make just a simple calculation so that we can save our computational time. So, but basically, we need to solve the basically, we get the potential and the acceleration. That's it. And for the hydrodynamics, yeah, we use quasi-Lagrangian hydrodynamics. I think you guys are familiar with the RFO simulation. So THESAN simulation and THESAN-Zoom simulation is based on RFO code. So this hydro part, what is this quasi-Lagrangian scheme? Yeah, to understand that part, I would say this way. So the previously Lagrangian scheme is camera is moving along with the fluid. And the grid-based or Eulerian scheme, the camera is just looking at specific area. But the yeah, area is not changing. It cannot be smaller, it cannot be larger. You're always looking at the same area all the time. But this quasi-Lagrangian scheme or moving mesh method, we are actually moving the camera along with the gas particles, but sometimes in the specific time, we can actually zoom in so that we can actually look at the gas particles movement more correctly, or sometimes we zoomed out so that we can see the more broad structure. So this is the easiest way to understand the moving mesh method. Alrighty. And also in DSAT simulation, we also included the radiation term. Actually, I should have put this. Let's go back to the equation, Euler equations. So if you want to make the radiation hydrodynamics, then you need to put additional radiation term in the momentum and the energy equation. Or if you want to put magnetohydrodynamics, then you need to put additional magnetic term over here and over here. So in this case, in our RFO, RT, or the DSAN simulation, yeah, we also included this radiation term in the hydrodynamics so that we can actually simulate the baryons movement of the interaction between fluid, baryon, and also photon. So yeah, photon as well. The whole specific thing, I actually made it from using some kind of AI tool, so you don't have to worry about this specific part. I just want to say that, yes, we included radiation part so that we actually try to reproduce the interaction between baryon and the photon. So that because our goal is reproduce reionization era at the high-res universe more correctly. Yeah. Now let's go to the DSAN simulation. So our DSAN simulation, the DSAN one, we have a box size of 100 megaparsec scale, which is around the size of the galaxy cluster. So when you simulate the decent galaxy, decent box, then you're gonna see lots of galaxies in it. And using that, we can make some kind of survey science or some statistical research. So for decent simulation, we want to know global statistics and also how the reionization era is happening. But sometimes you want to see individual galaxies movement, individual galaxies evolution as well. So that's why we selected 14 individual galaxies from decent simulation, ranging from low mass to high mass. So we just selected some 14 representative galaxies because we want to reproduce as diverse as possible. And then we run the simulation again, but with more accurate physics and more smaller scale. So in this case, the resolution of the THESAN-Zoom simulation is around 10 parsec scales. Still, it's still high, if you want to say that. Yeah, I think it's still high. I want to see more sub-parsec scale in the future. Yeah, it's compared to the THESAN or other simulations, this resolution is quite low. And the mass resolution is around the 10, 100 solar mass scale. Yep. In this case, THESAN-Zoom is more suitable for studying interstellar medium or circumgalaxy medium or galaxy evolution, those kind of things. So every simulation has their own purpose. So if you want to use the simulation data, yeah, try to look at those purpose more correctly. Yeah. Alrighty. So the main difference between THESAN and THESAN-Zoom is the selection of subgrid models. The gravity and the radiation and the hydrodynamics is exactly the same because the whole backbone is based on RFO code, but the subgrid models are just slightly different. So a THESAN simulation is based on illustrious TNG galaxy formation model. And the THESAN-Zoom simulation is based on smuggle galaxy formation model. The smuggle simulation model is more suitable for reproducing higher resolution simulation. So that's why we selected this smuggle model. So smuggle model can resolve the multi-phase ISM, like a hot ISM and a cold ISM structure more correctly. And cooling function is more accurate, more realistic, and the radiation is more, patchy or more localized, so that it's not uniform radiation. It's more like influenced by the local radiation source structure. And so that's why we can also resolve it better. Okay, so what we can get from the simulation. First of all, using the gas dynamics, we can get the gas information. So gas temperature, gas density, and the gas metallicity. And also at the same time, we can get the star formation rate. So if you are studying more interstellar medium or the circumgalactic medium kind of thing, then maybe you consider using this gas particle data. Or if you are studying more optical survey or those kind of things like emission line statistics or those kind of era, then maybe you can consider using our mock observation because we can also simulate the emission lines like H alpha, H beta, or the O3, O2, and 2. Yeah, those kind of optical emission lines you are familiar with. Yeah, we can also simulate, make the mock image as well. I think this is very unique thing about the THESAN simulation because we can directly compare our simulation result with the JWST or other survey science results directly. So yeah, this is the one of the topic one of our master students is doing at York University. And if you are studying more 21 centimeter or reionization physics, then maybe consider using photon density part because we can also recreate Lyman alpha flux from the galaxy and those kind of things. So yeah, you can also use those physics as well. And yeah, if you are studying metallicity or clumps, then maybe you can consider gas and metal information. Yeah, that's also what you can do. Alrighty. So once you make the simulation, Then the next thing you need to do is we need to see our result is correct or not. And this benchmark is always we need to compare it with the observation. Without matching the observation, our simulation result is just not super useful because what we are doing simulation because we want to simulate the universe and we want to compare with the observation. That's why we are doing that. So overall, I put so many pictures. I don't want to, to be scared by all those pictures. I just want to say that what we get is quite similar to what observation get. Of course, there are some discrepancy, and this is mainly because of the our resolution issue, because we cannot resolve a smaller scale structure very well. So that's why we can see some discrepancy, and that's why we see something. And also, I really highly recommend you to use the data, simulation data, and compare with the observation because whenever you find some discrepancy, that's the chance to study more because that's the part some physics is missing or our understanding is something not correct, and that's the part we need to study and we need to make it better. And one thing is missing because this is the stellar mass and black hole mass relation, and that's because this is my part. So I started this postdoc job at last October, which is almost 6 months. Yeah, my main research will be implementing black hole accretion, black hole model into the THESAN-Zoom simulation. So I'm still working on it. But the reason I didn't do a lot of work is because we are preparing for launching some other simulation, which we call it Lumina simulation. Yeah, our first papers are ready. It will be uploaded next week, next Monday. You will see it later. Yeah, this one is amazing because the size of the box. Yeah, previous decent simulation was 100 megaparsec scale. Now it's a 500 megaparsec scale, which is one of the biggest simulation we can see. And also we can track the redshift from 50, almost 50 to 3. The previous decent simulation is around starting from 30 to 5, but this one is a 50 to 3. And the resolution is still quite higher. So this is really nice opportunity to study more survey science thing. And the reason why I couldn't do my black hole physics yet is because doing I was writing the paper first Lumina set of papers about the 21 centimeter research. So when the after the dark age of the universe, around we believe it's around the redshift greater than 30-ish. And after that, the first stars are formed. We still don't know about this star formation, the pop three star, those kind of things yet. But we believe the star formation will be happening at around between 30 to 20. When the star formation is happening, then the Lyman alpha photon is going uh, emitted by the first sources, and this will change the neutral hydrogen fraction, and that will influence the 21 centimeter emission line, neutral hydrogen line. And that's what we want to simulate. Yeah, and that's what I have been doing so far. So yeah, I still need to finish my paperwork this week, but yeah, you will see that one at the end of the this month or early next month. So one thing I can show you is hydrogen and the helium ionization movie. So starting from redshift 30, yeah, you see the starting from the most center of the dark matter halo, a galaxy is formed, and this UV light it can ionize the hydrogen and the helium. Left side is the hydrogen, and the right side is the helium ionization. Here you see how the filament structure and the whole ionization history quite accurately. And this is one of the best thing that THESAN and THESAN-Zoom and THESAN and the Lumina simulation can do. Yeah, and I'm very proud I'm part of this team. Yeah, even though my name is not here yet. Okay, so yeah, what I have done is try to reproduce and try to calculate the 21 power spectrum because the power spectrum is what we will see from the observation when the next generation SKA and the Hera observation will make. Yeah, the left-hand side of the figure shows the hydrogen ionization fraction power spectrum. You see this dashed line over here. This is the THESAN-1 result. But now we see the solid line, which is the Lumina simulation result. They are not only quite similar, which means the resolution, the convergence is quite okay. And also it goes much further, which means because of the we are simulating the bigger box, that's why we can actually go further the lower wavelength. So yeah, this is one achievement we can make from the Lumina simulation. So the so this one can tell us about the ionization history. So the peak of this power spectrum, which starting from the redshift 9, this is the hydrogen bubble size. And when this one, as redshift goes lower, then the ionization is going onward. Then this peak of the power spectrum goes left and left. So left means the scale is getting larger and larger, which means the hydrogen bubble or ionization bubble is getting bigger and bigger, which confirms the inside-out ionization scenario. So this is something we can do. But the observation right now, the Hera or other, the 21 centimeter research, their upper limit is way above. So in the next few decades, we will see this 21 centimeter signal in the future. So yeah, one thing simulation can do is predict the observation as well. Okay. And not only that, the Lumina simulation can also simulate the helium ionization history as well. So for this one is the helium ionization fraction and the helium 3.46 centimeter line power spectrum. And when I only select the specific scale, which is 0.5, which is corresponding to around 10 megaparsec, and this is 2 megaparsec scale. 2 megaparsec scale, and how they are evolving over time. So using this peak, we can also measure the helium ionization bubble size over time. And that's how we can also confirm how the reionization, how helium ionization works. Okay, so so THESAN and Lumina simulation, what we can do is, we simulate the universe, we simulate the galaxy, and what we want to do is compare the JWST observational result with our THESAN-Zoom simulation result so that we can compare our physics. And the other one is using the ionization history. That can be confirmed, or we can study that using this SKA and the Hera observation as well. So this is the basic structure of the THESAN framework. I think this is the end of the part 2. So before we actually go to the data analysis part or data structure part, I would like to get some questions if you have any. Because part 3 will be very short. Yeah, I'm pretty sure you guys are better than me. Yeah, because I just gonna show you how to download it and how to read the data, how to plot it. Yeah, so it is very simple. Okay, well, I guess then I can just go to the part 3. So part 3 is going to be just a practical guide how to use the simulation data. Okay, so decent simulation data has some different three kinds of opposites. So first one is a snapshot, which contains every single particle's information. So you can think of it as the raw data. So it contains each particle's information, including position, velocity, and all metallicity and all those kind of things. This one is too heavy to use. So we made another one using group catalogs. So group catalog contains the information about the dark matter halo and the galaxies inside. So using the friends of friends algorithm, we first identify or the classify dark matter halo. And in the dark matter halo, yeah, you will see the galaxies are formed and they are made and they are interacting. We use the subfind algorithm to uh, identify those galaxy structures. And using this subfind algorithm, yeah, you can get the information about the galaxy properties. So mass of the galaxy, or the size of the galaxy, or the shape of the galaxy, or the metallicity, and all those kind of information. So most of the time, you will use this group catalog data. So I'm just gonna show you how to read those things later. And another thing, if you are studying Cartesian outputs, or the reionization history, or if you even want to make the movie kind of thing I showed you before, then I recommend using these Cartesian outputs. So in this case, it is distributed using the regular cell, just like a regular cell size, a regular uniform cell. So yeah, it is more suitable for studying or making movies or studying more background image or the ionization history. So yeah, this file is all saved as HDF file format, which is the hierarchical data format structure. So yeah, every information you need, like a box size of the simulation or the number of particles and redshift and the time information and the whole unit conversion, even the unit conversion thing is stored in header file. And the particle type has, yes, gas particle, and dark matter stars and black hole particles are saved as well. And yeah, and then those informations are, yeah, we try to provide as detailed information as possible so that yeah, anyone can use correctly, precisely. So yeah, if you see the later the guide or some kind of the tutorial on our website, yeah, you can see what kind of data you can use. Yeah, there are actually lots of them. I just picked up some of the most important things like density, the velocity, metallicity, star formation rate, or the black hole mass, accretion rate, and so on and so forth. So if you're familiar with using the illustrated TNG simulation, then the data structure is the same. So you don't have to worry about that too much. And for the group catalog, yeah, which contains the galaxy information, then you need to use this sub-halo part. Yeah, I will show you later. Yeah, this one contains the basic structure, basic properties of the galaxy. So you will see those things. And the Cartesian outputs, yeah, these things are just the Cartesian coordinate. And so it's good for making movies or studying a background or the radiation history. Okay, so this is the last part of the presentation. So how to read the data. What I want to say is when I first started this job, yeah, I wasn't super familiar with this THESAN and THESAN data set because I never worked with it. What I bothered was something bothered me a lot during that time, during the first time, is how to convert the unit because every simulation has their own unit and their own code unit and their own architecture. So changing to the physical unit is sometimes quite annoying. So just let me tell you something. Our CSUN simulation is saved as a HDF file format. And also this whole data is saved as a co-moving unit and also saved as a code unit. First of all, mass information is usually saved as a co-moving. Yeah, and mass doesn't change by co-moving scale. The unit is 10 to the 10 solar masses. So if you want to get the more precise unit, then you need to multiply by 10 to the 10. And another length unit, yeah, if you want to get the physical unit, then you need to multiply by scale factor A, those kind of things. So yeah, this is the thing many people miss. So but even though you miss it, sometimes the result looks similar, but something is slightly different. You cannot tell the difference quite subtly. So I want you to make sure that, yeah, be careful about the unit conversion. Okay, so that's all. I'm gonna show you yeah, how to download the data because that's the most important part. If you go to THESAN, yeah, just search the internet, yeah, type the THESAN, then you will see our official website. And if you want to, yeah, if we want to use the THESAN data, then first of all, yeah, please contact me. I will more than happy to help you. Yeah, how to read the data and how to understand the data correctly. But if you want to just download the data and just look at it, just then I recommend you to use this global system. Yeah, we already
Sorry,
uploaded every.
sorry,
Yes.
just we don't see the full screen. I just see the top bar. Let me try sharing
Okay.
again.
I am so sorry. Yes. Uh, why is it happening? I think now it will work.
Yep,
Is it
there you go.
right?
That's good. Yeah.
Yeah, thank you. Yes. So yeah, from my side, you can go to Globus, and I already logged in. So you can go to a file manager and just type DSAN. Then you will see different things. So this one is containing the initial condition. If you want to run the simulation, then use this initial condition. But if you get the simulation data, then you need to click this descending. Yeah, we have lots of different kinds of descent derivatives, and those things are high resolution or dark matter only, or descent 1 and descent 2. So I'm just gonna use this descent 1 data. Yeah, you see output and post-processing. If you want to make a movie or some kind of things, then yes, this sorry, this post-processing data will be useful. But if you want to use the survey data or galaxy properties, then I recommend you to go there. The group data. Yes, the group data has lots of other files as well. So this FOF subhalo table is the group catalog. So when you download it and when you open it, then you will see the galaxy information. Yeah, let me just change one more screen, and that'll be the end of the presentation. So if you actually download the HDF file, I just opened some random HDF file, which is the group catalog, and you see the whole structure. Yes. Yeah, this structure has a header file which contains the whole simulation information, and this is subhalo structure, or you can say directory. Then you see lots of other information, including black hole mass and the black hole accretion rate, and the subhalo, which is the galaxy metallicity. Yeah, in this case, galaxy metallicity, and the half mass radius, and which is the size and the position, star formation rate. Yeah, this one is the unit of the star formation rate is solar mass per year. I think I picked the low redshift, so that's why the star formation rate is quite low. Yep, and this is how you can use the data. And if you want to plot all those things, then yeah, please let me know. I have a bunch of the code to the visualization, so I'm more than happy to provide it. Okay, so this is the end of the presentation. Thank you so much for your attention. I'm happy to take any questions. Okay, I will go back to the slide.
So thank you so much. I see claps in the chat. Yeah, if anyone has any questions, you can either just unmute yourself or enter them in the chat. We have one question. How can you
Yes.
visualize the concrete galaxies?
Oh, yes, that's a really good question. So for yeah, to visualize the galaxy, we need to use we need to use there are two ways as far as I remember. One is the using Cartesian data, and because it has the whole information, what was that the unit band, the optical band and all the information, you can just plot it and then it will make the whole galaxy structure. Or if you want to be more precise or look at the 3D structure, then I recommend you to use the snapshot data because the snapshot data has lots of the old gas particles, star particles, and including the metallicity. So you can actually customize it. So using the higher metallicity stars, then this star particle should be redder. And also according to the temperature of the gas, also you can change the color scheme. So you need to, I think that way, using the snapshot file will be much accurate, much suitable for the visualizing the galaxies. And also there are lots of tools as well. I remember, I forgot the name of the whole thing, but yeah, many of the simulation and many of the simulation data has their own visualization tool. I think we also have some kind of visualization tool as well. So it sets you the smoothing length, which is the how to set the resolution and how to set the color scheme. If you put the whole these things and select the which galaxy you want to visualize, then you can make it. Yeah. Actually, I haven't done it before, so I'm not super familiar with this part, but every simulation has that kind of thing because I saw, yeah, some of the our collaborator made it, so yeah, there must be a way to do that. Yeah. Okay, you're welcome. Yes.
Hi, it's Solvay from the University of Calgary. Really nice talk. I had a question about your work that you're going to do on the black hole
Oh,
host scalar
yes.
relation,
Yes.
like what that will look like in the simulation.
And so right now, what I'm trying to do is, yeah, during my PhD, what I've been doing is implementing black hole physics into the another kind of cosmological simulation. So what I did is usually most of the cosmological simulation, they use the most simplest format. So the equation physics, they use the Bondi equation, which assumes the gas particles are surrounded the spherical shape and they are just going in. But when you look at the universe, that's not actually true because we already see the existence of the equation disk, not spherical shape. So what I have done is implementing another kind of accretion model, which is alpha. We call it the standard disk model or alpha disk model. So I already implemented it, and this is the one of the galaxy result actually. Yeah, I tested several things, and it falls into the black hole scaling relation quite okay. And another equation model I also implemented is torque limited equation. So when the gas particles are surrounding and rotating around the black hole, it will lose the angular momentum, and that's how it goes slightly falls into the black hole. And that kind of physics is already quite known. So I also want to implement. I'm right now implementing that kind of equation physics into the THESAN Zoom simulation. And another thing we can do is the how agent feedback work because this one is so unclear area. So yeah, many of the simulation they use the first of all, when the accretion rate is high, then they use the thermal feedback, just like a quasar kind of activity, just to put the whole energy as a thermal feedback. Or when the redshift is low and for especially the higher mass elliptical galaxy, we see some kind of radio jet is coming out. So for low resolution, then we can also try to the low accretion rate, then we can also try to I'm trying to put that kind of phenomena into the THESAN-Zoom simulation. Yeah, right now I think the THESAN-Zoom's black hole physics is not super accurate, so that's what I'm doing right now. And once this one is correctly done, then we can actually see how black hole feedback is influencing the interstellar medium or even goes further the circumgalactic medium, this is what I want to see. Yeah. Or if it can also influence the galaxy evolution or star formation history a little bit as well.
Oh, cool. That's going to be very interesting and exciting to see when that's implemented.
Yeah, I'll do my best to get it done as quickly as possible. Okay, any other questions?
While people are thinking of questions, I have just a quick one. The new simulations that you guys are coming out with in the next few days,
Oh,
basically,
yes.
will these also be accessible in the exact same ways as the rest of the THESAN
Oh,
simulations?
so right now we are discussing it. So THESAN 1 and THESAN simulations are yeah public. So you can download it on Globus. And THESAN Zoom simulation, actually the first paper is not published yet. It is uploaded, but it's in the review process and it's been very long. Yeah, since I don't know who's reviewing it, but it takes really long time. So after it is officially published, then we are thinking of uploading it and publish it online. It will be end of this 2026 or early 2027. And for the Lumina simulation, which is this guy, so just like a observation, because yeah, when you make the new telescope, then most of the time the operators and developers take the time, most of the time for first few years. We do the same. So our collaborators use the simulation data first for the first 1 or 2 years, and then this everything will be public. So I think the public access will be in the early 2028, but they are discussing the timing. Yeah. But if you want to work with this Lumina simulation and Lumina project, if you want to look at something, then you can collaborate with you can collaborate with the THESAN project or the Lumina project members, and you can access to the data. Yeah, this is how I understand this is how research work. Yeah.
Thank you. Does anyone else have any questions? Just raise your hand or put it in the chat. Let people think for a second. Um, yeah, okay. Last chance, any questions? If not, I think we can go ahead and thank our speaker again. Great talk.
Right. I'll stop sharing. Thank you so much for your attention.
Yeah, thank you guys so much for attending. Great attendance today, and thank you so much for the wonderful talk. And I think we can wrap things up. So keep an eye out for the recording of this. Will be posted on YouTube and shared with everyone. And yeah, we'll see you guys all again soon, I hope. Thank you guys.
Thank you.
Thanks.